Welcome to lecture 6.3. In this video, I'm going to show you another strategy for trickier integrals where you can't see the antiderivative at first glance. And this strategy, which is formally known as integration by parts, is one of the more powerful tools that you will have for tackling these integrals. At its core, integration by parts is actually just the product rule, but we're kind of putting it in disguise, looking at it from an integral perspective instead of a derivative perspective. Let me show you where it comes from, and then I'll show you how to use it. So on this line here, you can see the product rule. This is just the normal product rule that you're used to. If you start with a function u times v, and you take the derivative of it, we've seen many times that you can't just take the derivative of u and multiply it times the derivative of v. You actually do this other thing that involves adding two terms. So in derivative notation, the derivative of u times v is u dv v du. Well, in integral notation, that's the same thing as saying the integral of this side of the product rule equals u times v. The original function is the result of the integral. These are kind of opposite statements. So thinking about the integral notation version of the product rule, we know that there's something called the sum property, which allows us to split this integral into two pieces. And then we can rearrange this expression just by subtracting the integral of v du to the other side. And what we get is this expression. This is called the integration by parts formula. Now, as far as you're concerned, you may not really understand why I subtracted that integral, but you should understand that I can. I just subtracted it from both sides, and this should clearly be an equivalent equation to this one. So it turns out that this format is really useful. And it's useful in situations where you're looking at taking the integral of two things that are being multiplied times each other, but aren't necessarily related. U and dv are the original function and derivative of two separate functions. So the basic overview of integration by parts is you're going to look for an integral that is a product of two other things, and then you're going to identify u and v and du, and you're going to rearrange those pieces to create a new expression, and this right-hand side expression is somehow going to be easier to evaluate. Let's look at this in practice. Here we have an example where we're trying to take the integral of a function that is essentially a product, two things multiplied times each other. Notice that substitution won't work here because I don't see a function next to its derivative. So we're going to use integration by parts. The first step in integration by parts is to identify u and dv. In this example, I'm going to choose the function x to be my u function, and cosine x times dx is going to be dv. On the next slide, I'm going to help you figure out how to make this choice. For now, I'm just going to show you the process. The one thing that you should pay attention to is that the dx is always going to be part of the dv. So I could have chosen x dx to be my dv, but I could not have just chosen cosine of x to be my dv. The dx has to be part of dv. So I make this choice. I'm choosing what u and dv are. And then based on my choice, in order to use the right-hand side of the formula, I'm going to need to figure out what v should be and what du should be. When you do this yourself, you're going to want to set up a space off to the side or at the bottom where you can notate this. So I know that u is x and dv is cosine of x. I also recommend that you set it up kind of in a square like this, where u is next to du and v is next to dv, which will just help you keep organized and probably help you use the formula. So if u is x, du is the derivative of u, which is just dx. That direction is usually pretty easy. If the derivative of v is cosine x dx, what would v have to be? That's right, it would just be sine of x. So as of right now, I'm all set up and I'm ready to use the product rule formula, the integration by parts formula. As the answer to this integral, or the first step towards the answer, I'm just going to follow this pattern, and I'm going to start by multiplying u times v, and they're not inside an integral anymore. That's just normal u times v as a function. So u times v is x times sine of x, and then I'm going to subtract the integral of v times du. And this, in essence, is the integration by parts formula. Now, you're not done until you've fully reduced the integral. And what you should notice is that although we still have an integral in our answer, this is actually a much easier integral to evaluate. This one was pretty complicated. The integral of sine is a pretty normal function to integrate. It's just negative cosine of x. So once you evaluate that second integral, you can distribute the negative symbol, and you end up with your final answer. The interesting thing here is you could, if you wanted to, take the derivative of this expression. Notice that you'd use a product rule here, and when you take its derivative, you're going to end up with x cosine of x. You can verify that if you like. All right, so let's try two quick ones. And for now, I've told you what to use as your u and your dv. All you need to do, if you review those steps, are identify v and du, given u and dv, apply the formula, which is up here for your reference, and then simplify the integral that you get. Go ahead and try number 1. Perfect, so now that you know what v and du are, go ahead and use these 4 places to use the integration by parts formula and evaluate and solve to get a final answer. The work looks just something like this. Go ahead and start number 2. What are v and du? Yep, again, du is usually pretty easy. If you didn't get the 1/3, try taking the derivative of v. You should see that you get this expression here. Now that you have all 4 parts, put them together and tell me what the answer to the integral is. And your final answer would look something like this. If you missed the 9 on the bottom, think about using a little u substitution right here to help you handle the 3t. Some of you will start to be able to do that in your head, as I have, and then don't neglect the flipped sign. The actual antiderivative of sine is negative cosine, and then a negative and a negative made it a positive. Okay, from here you should basically understand that integration by parts is just applying this formula, and you will need to memorize that formula. The tricky part is not the formula, it's choosing u and dv so that it actually works out. Think about the examples that we did. What happened each time when we took the derivative of u? What happened that made the second integral easier than the first? I'll put this second example up so you can see it. Right, in all of these examples, when we used the integration by parts formula, the new integral was easier because in some ways that original function disappeared. When we took the derivative of 2t, it became just a constant or a coefficient. When we took the derivative of x in this example, it went away and just became dx. So this is actually a clue for how we can choose, and that's the next step, is making sure that you know how to choose. Here are some general guidelines. You should pick the u function so that when you take its derivative, it either disappears or its power decreases so that you could maybe repeat it and get the same thing to happen later. dv should have an easy antiderivative. If you pick something for dv that doesn't have an easy antiderivative, then when you go to find the actual v function, you're going to get stuck. And then the last guideline is that when you're picking u and dv, everything in the original integral needs to either be part of u or be part of dv. You can't have an extra exponent or an extra dx left over. Everything has to be either part of u or part of dv. So go ahead and use those guidelines and see if you can identify what should u and dv be for these 3 integrals. Nice. These are the choices I would have made as you saw in Edpuzzle. I'm guessing the last one may have been the confusing one. One hint that you should choose ln to be u, not dv, is that you can't take an antiderivative of ln. We can take the derivative of ln, but we don't know an antiderivative. So if I had tried to use ln for dv, I would have gotten stuck, and that's why I chose it for u instead. Now that you know the correct choices for u and dv for each of these 3 examples, see if you can use the integration by parts formula to finish evaluating all 3 of these integrals. So you saw the answers in Edpuzzle, but here's the work if you'd like to double check what you did against what I did. Notice that in example 4, I used u substitution to help me with tangent after already using integration by parts. And then in the last one, when you put together v du, you can actually simplify this expression first, which makes the antiderivative a little bit easier to take. This will obviously take some more practice, but I want to look a little bit more specifically at two cases where you definitely want to use integration by part, and that's log functions and inverse trig. Given the guidelines for choosing u and dv, when you see a logarithm inside an integral, do you think it should be u or dv? Exactly. Log is always going to have to be u, and that's because we can't take an antiderivative. So it has to be u so that we can take its derivative. In this first example, we would have to choose log base 2 of x to be our u value. Okay, so that means dv has to be everything else, including the dx. So dv in this example is going to equal 5x cubed times dx. From there, we just follow the normal integration by parts steps. The next step is to figure out what du and v are. You may need to look up the formula for the derivative of a log with a different base. You'll notice it's just a matter of adding an ln of 2 in front of the expected derivative 1 over x, and then take the antiderivative of dv, which should be 5 over 4x to the fourth. And now we set up integration by parts using the formula. U times v is 5 over 4x to the fourth times log base 2 of x. And then we subtract the integral of v times du. And notice that I caught myself missing the dx, so I tacked it on there. Now I'm going to simplify this expression and take its integral. Keep in mind that ln of 2 is just a number, so this is going to be part of the coefficient 5 over 4, and the x variables are what we really want to focus on when we take our antiderivative. And keeping in mind that this expression is still just a number, we can go ahead and take the antiderivative and simplify to get an answer that looks like this. It's messy, not too complicated. Try one for yourself. This one down here. And here's what my work looked like if you need to check any of your steps. So just like log functions always have to be u if you're going to use integration by parts, inverse trig functions also always have to be the u because we don't know antiderivatives for them, we just know derivatives. Look up the formulas if you need to have them in a separate tab. Here's what example 1 looks like. For reasons I just explained, u has to be the inverse sine function. But the weird thing is that means the only thing left to be dv is just dx. That might seem a little weird to you, but it's actually perfectly fine, and it makes finding v really easy, because what function has a derivative that's dx? Well, just the function x, like the stupidly easy example. The derivative of the inverse sine function, maybe you looked up or remembered from class. Now that we have all 4 parts, we can set up our integration by parts formula. And this integral, which might initially look more complicated to you, is actually a perfect candidate for u substitution. If we choose u to be 1 minus x squared, then du is negative 2x dx, or more importantly, x dx, which is what we're going to substitute for, is negative du over 2, just from rearranging that. So here's how I can rewrite my integral using u substitution, which is a different strategy than the one from this video. This is yesterday's strategy. We get negative 1 over 2 root u du. The negative 1 over 2 came from this piece tacked on at the back. Now I anti-differentiate using the u variable and convert back to x's for a fairly simple looking final answer. Notice the u came from right here. Don't get it confused with the original u. See if you can replicate this work to do the tangent example. Your work should look something like this. Please pause here to make sure that you understand each of these steps. So as you may have gathered from this example, one of the tricks moving forward is to make sure that you know how to tell when to use integration by parts and when to use substitution. This is where we'll end for today. Take a look at each of these. Keep in mind that we generally want to use u substitution when you see in the function a function and its derivative, and you see them both. When you see 2 different functions being combined, or a function that's hard to take an antiderivative, that's when you use integration by parts. Lovely. Take a moment to understand your mistakes if you got them wrong, and don't forget to post a comment to the website.